Hello and welcome back to my tutorials. As you can see, I improved my setup. I have a microphone, I have some lights. This is amazing. I hope that you can listen to me better. I still have some problems with the keyboard sounds and well, I'll fix them later on. But I hope this brings to you better quality. Shout outs to Herman. He has been really helpful for this tutorial since I learned plenty of stuff in the last couple of weeks. And I want to show you guys. So let's begin to create this effect. So let's get started. First of all, we create this geometry node and we add a box. We usually, as always, copy the parameter down below and divide it by 2. There we go. Then we press enter and we make the box larger, like so. Now we want to make a building that goes upwards, so we should create a boolean. Why? Because we want to have the inner part empty. So let's create a transform now. Now we want to scale this down on the X and Z position, 0.8 and 0.8. If we go to the boolean, we will have this previous. So this is okay at the moment. Then we add a copy and transform, and we copy the height. We can apply it here also on the height and create a big column. Let's see how it looks with the poly wire, with the wireframe. Then what we should have is the UV unwrap, because we might want to shade it after the fact. You can obviously use a UV quick shade to see how it looks. It looks fine. After we have this, we need to create an activity node, because we're going to create, as always, if you watch my other tutorials, the names of the objects we are going to break. So use primitives, create a wrangle. You already have my setup. Sorry for this. I already have my setup right here. We go and we set names. We have s at name equals piece plus integer to string of the class. The class is the following. So if we have, let's say, 2 pieces in primitive, we will also have 2 pieces, 3 pieces in this case, in the name. This will be called a building. See, it works. Now we need to create a fracture, a boolean fracture, and we need to create the cuts. We're not going to use material fracture because that's not the way to do it, or not the correct way to do it. So let's create some grids. Let's scatter some point on the ISO offset of the geometry. Let's add a 100 resolution and let's scatter, let's say, around 40 points. Now we want a really big grid, for example 40 by 40. Maybe this is a bit too huge, but it's always good to be sure about it. And let's do a copy and transform, sorry, a copy to points. See, we connect the points to the points and the grids to the grids, and have some scatter grids here. If we connect this to the boolean fracture, we're going to have these fractures. It works just fine. We can press Ctrl and middle mouse click and person name to see how it changes. What we want to have now is a random attributes on the points. We will use the normal like this. We have now a different result, But we will go to direction and orientation. Now we have a really nice result. We can use, obviously, a mountain noise, just in this case. We're going to keep it simple. You can obviously make it more complex. Let's add, I don't know, 5 height. We can preview this here. It looks fine. Maybe we need a little bit more resolution. We can use a subdivide. See, more result. This is better. And we can have more height. Let's say 10. But the element size will be smaller, like this. I mean bigger, so we have a low frequency noise. If we could add more and we increase this even more, they are like waves. We add a new mountain sub. We can make this the other way around. For example, 1 and let's say 2. We will add more definition so we can see what's going on even better. Maybe 1 more. There we go. See, this is working just fine. There we go. Something like this should work perfect for this scenario. Now, if we wouldn't fracture this, we will have, after it fractures, a really nice geometry. See how this looks? For this tutorial, this will work just fine. So let's continue. We will append the name here with this tag. So we're going to have the building, and I am missing the original name because we have the pieces, but we don't know where it belongs to. So we will create ds name orig equals to the name, and we will wait again for it to fracture. Now that this is fractured, we are going to assemble this. Assemble. If we assemble this, it means that we're going to have packed geometry. You still have the geometry here. Look, exploded view. We do have it. In fact, it looks quite nice. We need to fix some stuff, but to start with, this is really fine. And we are also going to do a poly reduce because we want a proxy geometry. We're going to use half the polygons. Now we're going to simulate with this. See, we had 6,000 points and before we had 22,000. This will simulate way faster. I might even go to 75% because we don't have that much information. So we will also assemble this. After assemble, we're going to create a frame and make these pieces smaller, just a tiny bit, because we want some space, some padding in the simulation. 0.95. Okay, we're going to delete channel. There we go. Okay, let's do a quick test on this. So we're going to create a dot network where I'm going to create a null that says out proxy. Let's go to the geometry and create the RBD path object and connect this to the proxy. This is the proxy. Nothing happens because we still don't have anything. So we're going to create a reissue body solver. Let's connect this here. Let's add some gravity. Let's add a round and merge it on the pipeline. So if we press play, this works. It's intended. Obviously, we don't have any type of constraint, so it just gets destroyed immediately. So we don't want that. So let's create, after this, the conetwist constraints. This is going to be the hardest part of the tutorial, but the best part. We unpack this and we leave this base in the inside group. We'll only have these inside groups. Let's scatter some points on the surface like this. Let's add 1 million, 100,000, sorry, and let's connect adjacent pieces. We need to transfer the name and we need to scatter the pieces. Now we have the name in the points. So if we connect this, we can see that each primitive has its two colors, the piece A and the piece B. We can have one connection and maybe search with 2 points. And we can add 1 million points. This will create more polylines, more primitives. We have a lot, 130,000 points and 22,000 polygons. Let's also delete some of these. Let's add by range from, let's say, 30 to 35. Now we have 10,000 points. Let's crank this up a little bit more to 45. Now we have 8,000. This works just fine. One more thing that we should do is to make a facet. So we split each primitive. We can see, okay, it wasn't necessary in this case. Oh, sorry. Now we see the difference. Yeah, we have more points. And always add clean. The clean is to delete and use points. We don't have anything yet, but it's always a good practice to add a clean now after the fact. So create a wrangle. We should, okay, one more thing. We should usually add the restlength. We're going to delete it after some settings, but always try to have the restlength. So first of all, we need to know what constraint we're creating. This is going to be a constraint name equals cone. It will also be a constraint type that will be all, so it has all the configurations. And one more thing that we should do is to create the goal of the axis of the cone. The cone is, imagine a cone that has a stick in the middle, and the stick can move inside that cone. Well, we need to have that information. And how do we control the direction? Where it is that direction? So the direction is basically at the normal. If we add a poly frame, we can connect this here, and instead of having the normal name like this, we're going to change tangent U for N. Now we're going to use that information for the following. We're going to create the constrained twist axis. This will be equal to the vector of the normal. This has to be a vector. And we will also have the constrained up axis. We also need to have the goal where it has to be restricted by. So let's copy this, and instead of constraint up or goal and goal, we only need to change the goal at the up directions for the up vector, and the up vector will be equal to the following: vector up equals set of 0, 1, and 0. Okay, we have everything set up. We can add some more stuff that we are going to be able to see it inside the dot network. And these things are 3 more variables. Every variable is a float. They will be the max up rotation. That will be set to CHF of max up. We will also have max out rotation. That will be set to CHF to max out, and we will have one last thing set to max twist. DHF max twist, and we should be set up here. We will have this. Let's play with 20, 20, and 20 just to begin with, and let's create a node that has con. Now let's plug this constraint with a constraint network. If we connect this and create a twist relationship like so, we will use $os and call it con. We will see we displayed the geometry and we place everything to 1, 1, 1. We should be start seeing everything. If we go to primitives, don't forget to use primitives here. And one more thing, promote. We created a normal. We should promote the point of the normal to primitive on the first match. Now, if we load everything correctly, and here use the out constraint, we should see everything. See? Everything is working just fine. How do you know it's fine? Because the light blue line is inside the cone, and on top, perpendicular to it, we have the green inside the yellow triangle. We're going to reduce the guide just a tiny bit, like so, so we can see a tiny bit better. There we go. Okay, so let's see how this works. Let's display the geometry and let it fall. Everything is attached, but it is like wiggling or twisting or something like that. It won't ever break. Okay, so this setup won't ever break unless we have a subsolver. Subsolvers are great, really good for constraint geometry. So to start with, if we go to primitives, we have an angle that will become really useful now. Let's add a wrangle attribute, set it to primitives, and let's watch it. So we're going to be working on the constraint name, any name that has on inside, hence every constraint at the moment. We're going to create an if function, and we are going to say, okay, so if the angle is bigger than the float of max angle, we are going to remove prim of 0, prim num 1. This is the full code. This should work. Let's play it. Now we have 0, so everything breaks automatically. But if we add a parameter interface and we add at the bottom a float, we're going to name this max angle, like this, max angle, and here max angle. Apply, accept, copy parameter, go inside, and press on this node, on this button, sorry, the relative reference. Now we go here and let's say at point 1, not everything is going to break. Look, this is resisting. So here it's starting to break a little bit. It broke here, and this is more organic. Right away, this is more organic. It's working, but we have a little problem. Not everything is working as intended. Why? Because we should do a little modification to the constraints. First of all, we need to create a prim make every constraint a tiny dot. So let's add 0, 0, 0. We don't have anything here unless we set this to display points. And since this is infinite small, we're going to change the restlength to 0. See? As intended. I already have this saved, so if I wrap the conetwist, it should be the same. See? It's the same. The names are swapped, but it is basically the same. I'm going to leave this code pasted down below. Now if we go back in, everything should work just fine and even better. This is used to avoid explosions. Sometimes the simulations don't work and explode out of the blue. Okay, so we have this. We can play a little bit more, let's say 0.4. Now press play. See how everything started to break earlier. It works amazingly. And we can go a little bit lower on the threshold, and well, this is going to break almost immediately. See, we can control the break threshold so good. Now we want to make this even more complex, so let's create based on the same thing, based on this new constraints like this. Everything is okay. We can even copy the same. Okay, so we can actually copy everything up to here, because it is basically the same setup. Maybe we can add a different scatter. See, this is scattering, just so we can change, or yeah, it's just so we can change the relax. Okay, so this is going to be way easier. Let's create a wrangle. This will be s constraint name equals to spring, and then we'll have an s constraint height equals to all as before, and f strength equals to 1. This is all you need, and we're going to merge this. In this case, we don't need to add a primitive. This will work just fine. Always set it to primitives. We should be able to see here, if we have a spring constraint relationship, do $, and set it to spring, we should have more constraints, as we can see. Let's only use this one, and let's add a really strong strength. Let's go more progress with the more slow with the iterations. See, everything is taking kind of together. See, it's moving all together. We can go up to crumble. Okay, this is fine. So we can add a second attribute wrangle, and in this case it will be to the spring, and this will be based on if the distance is bigger than the rest length multiplied by chf and mult. This should work. We're going to delete the first one with a delete parameter and apply and accept. Let's go backwards and create a new float. We're going to move it down below. It will be mult spring mult spring. Apply and accept. Copy and go inside and set it to here. Now we have this and this. And we have two ends here. Now we should see that everything breaks immediately. And if we add 1.1 and reset the simulation, we should have this working just fine. See, there's starting to get compressed, destroyed. We can play with this number. Let's set it to 2. Some constraints are starting to break due to pressure. Some are also holding. Maybe we want some more resistance. This is going to be, I believe, fine. Okay, so let's see how this looks with the geometry on top of it. It's working similarly, but not quite so. So, if we're going to merge both of it, we will have the following. Let's go to frame 84. So if we take a closer look, the constraints are breaking on a really interesting fashion. And it's starting to look really cool. Then that we're going to create will be the connect adjacent pieces based on this attribute, and we're going to find the name reach. So we're going to connect these two. In this case, we don't need anything else. This is going to be a regular glue constraint. And that's about it. Let's connect this here. Let's go inside. And let's add a glue constraint relationship. $2. It will be named to glue. Let's connect it. Now we have clusters. See, the building is holding together way better. Let's check the constraints just for a minute. We can see. I don't want to display this. I don't want to display this either. We have the glue here. These are the red lines. These are the ones holding the top and the bottom together. Let's show the geometry and let's see how it goes up to frame 48. So I went to frame 144 to check how it looked, and we can see that it has 3 different layers because we're connecting the top, the middle and the bottom together, and it's crumbling in a really cool and interesting fashion. Points like this. We have everything here. See how it collapses? Usually we're going to just need the RBD, the bird, and we're going to transform pieces using this node and this node. And now we have the final result. This is amazing. This is just so beautiful. I hope that you enjoyed the tutorial. I'm trying to bring the best quality in this couple of ways. I'm changing lots of stuff. I changed to English, I changed the lights, I changed the microphone quality, everything. So if this works better, please don't forget to subscribe, join my Discord, you can follow me on Twitch. I'm going to be present everywhere. So I hope that you enjoy it again and see you the next time.